Okay, so let's get started here. In the last class, I was speaking in kind of an abstract way about states of any system without saying what system or what kind of states. I think at this point I need to get more specific and talk about particular examples. So I'm going to begin with a few classes talking about a model for magnetism. Okay, so this is a famous model for magnetism called the Ising model. I should say this is a model that's, of course, named after a person, Ising, who developed it. He was German. He pronounced his name in the German way, of course, which is Ising. But Americans normally say it wrong as Ising. And you guys are in America now, so you have to learn to do things the American way, even when it's wrong. And so I'm going to be saying Ising here. Okay, so the idea here in this model is that we have a lattice of magnetic moments. Okay, so you could imagine, for example, a crystal full of magnetic ions. Okay, and in this simplest model for magnetism, each of the magnetic ions has two possible states. Either it can point up or it can point down. Those are the only two possibilities in this simple version, right? We're going to forget about the possibility of pointing sideways or diagonally or anything else. Okay, so we're going to make a lattice like this, okay? And for each site of the lattice, there is going to be some arrow. And this arrow represents the local direction of the magnetic moment. And it has, as I said, just two possibilities, either up or down. Okay. So each of these arrows is a magnetic moment, and it's commonly called a spin. Okay, and it's called a spin for reasons related to quantum mechanics. But if you haven't studied quantum mechanics, don't worry about it. We'll just call it a spin. Okay, and so we represent it graphically by an arrow up or down, and we could represent it mathematically by a variable sigma sub I on the site number I. Okay, so I means which site of the lattice. So for example, let's think about this site. Okay, so each site gets some site number, and then there is a spin on that site. Okay, and the spin is either +1 or -1. Okay, so +1 means up and -1 means down. Now, there are two important influences acting on the spins in this lattice. Okay, so one important thing is that the spins tend to be aligned with their neighbors. Right? So because the spins tend to be aligned with the neighbors, we want to say there's a nice, favorable, low energy if the two neighboring spins are pointing the same way. If they're both up or they're both down. Okay, either both up or both down is good. That's a low energy. By comparison, if one is up and one is down, that's bad, right? That's an unfavorable energy. Okay, so if we look at the the nearest neighbor pairs, right? Okay, that's 2 ups. That's a favorable negative energy. Here's a pair where there's 1 up and 1 down. And so that's unfavorable. Okay? So one way that we could represent that mathematically is to say that the energy has a term which looks like the product of the spins on neighboring sites. Okay, so if these two things are both +1 or both -1, then you get a positive number here. Okay, but if they're different, one's plus, one's minus, then you get a negative number. Okay, so we want to say that the energy is some negative coefficient, which people usually give the letter capital J, okay, times this product. Okay, so you get a nice low negative number if they're both plus or both minus, and you get an unfavorable positive number if one is plus and the other is minus. Okay, next, what else do we have? We have, this thing has to be, of course, summed over all the nearest neighbor pairs in the lattice. Okay. So whenever we have a nearest neighbor pair, that means a pair going sideways or up and down, okay, that goes into the sum, right? But if you have two sites that are like there and there, those are not nearest neighbors. Those are farther apart, so those don't count. And that's written mathematically by saying, whoops, I need my pen, by saying that we have a sum over sites I and j in angle brackets. And that's just a notation which means that I and j are nearest neighbors. Can you see that? Yes, of course you can, because you see the same thing I see. Okay, good. So that's one important term in the energy. Okay. Now there is a second important effect, okay, and that is that there's an applied magnetic field. I'll put that in blue, okay. So let's suppose that we put on a magnetic field. And that influences every site in the whole lattice, okay? And each site tends to be aligned with the magnetic field. Okay. And so that means if the magnetic field is pointing up, then the sites have a nice negative energy if they're also pointing up, okay? And they have an unfavorable positive energy if they're pointing down, right? And vice versa if the field is down, right? So one way to represent that is to say, let's have a field H which interacts with the individual sigmas. Okay, so if H is positive and sigma is positive, that makes a negative energy. Okay, and if H is positive and sigma is negative, it makes a positive energy. Okay. And this has to be summed over every site in the lattice. Okay, so I make a sum over the site index I. All right, so this is the Ising model, okay? And so it is to say we have this lattice of spins and there's an energy associated with the lattice. And this expression here tells us how to calculate what is the energy. And I should say that this lattice could be in any spatial dimension, right? So I have drawn it here as a two-dimensional lattice to go onto your two-dimensional screen, but it could be a three-dimensional lattice. It could be a four-dimensional lattice. It could be any dimension lattice, right? And it could be any lattice type. That is, it could be a triangular or hexagonal lattice instead of a square lattice. We will neglect the edges, okay? That is, we'll assume that it's an infinite lattice that goes on forever. So there's no boundaries to worry about. All right, so now that we have this model, we could say, what do we want to do with it? Okay, so what we want to calculate is the magnetic order. That is, how well aligned are the spins? Okay, how well aligned are they, and in what direction are they aligned? Are they mostly pointing up, or are they mostly pointing down? Okay, so one possible state would be a state where almost everything is pointing up. Maybe there's an exception somewhere, right? But this is a state that is well aligned, pointing in the up direction, right? Or there might be a state that is well aligned, pointing in the down direction. Again, maybe not 100%, but mostly in the down direction. Or there might be a state that has some of the spins up and some of them down, so that it's approximately 50-50. Okay, so we want a mathematical quantity that can distinguish between these different possibilities: well aligned up, or well aligned down, or not so well aligned. Okay. One simple possibility to distinguish among these things is to say, let's look at how many of the spins are pointing up and how many are pointing down. Okay, so suppose there are n spins in total, and we'll count how many of the n are pointing up or pointing down. Okay, so we'll say there are n up that are pointing up, and n down that are pointing down. Okay, and of course that's all of them, right? So that n equals n up plus n down. Okay. So the thing that we could calculate might be, what's the net number? How many up minus how many down? Okay, so if we look at n up minus n down, this is a good way to distinguish among the different possibilities here. Okay, so if we take n up minus n down divided by the total n, okay, and we average that, okay, that is going to be a definition of the magnetic order. Okay, I'll put a box around that. Okay. So this thing we'll call our magnetic order parameter. Or people would sometimes just say the magnetization of the system. Okay. Please, question.
I think this description doesn't distinguish two special possibilities for the configuration of the spin, right? If the half of the system is spin up and the other half of the system is spin down, and then the total magnetization is 0, right? However, if the spin up is distributed randomly in the system, and the other half of the system with spin down also distribute randomly in the system, the magnetization is still 0, right? I think
that's right. And so, I mean, this is one bit of information about the system, but it's not the only thing that we could calculate, right? And so we might want to do better than this, right? We might want to know about whether the system has different regions, like you're describing, right? So one region that's all up over here and another region that's all down over there. Yes, but we have to start somewhere. Okay. So I'm going to start with the simplest thing right here, assuming a spatially uniform system. And indeed, I will get to more complications coming up later. Okay, but excellent point. Thank you. Okay, so for this magnetic order parameter, we would say, for the picture on the left, the magnetic order parameter is approximately, positive 0.9. And over here, it's about negative 0.9. And over here, it's approximately 0. Okay. So in this simplest level, I want to just characterize the magnetic order with this one number, okay? And so this is the kind of number that somebody might measure experimentally, right? If they're doing some kind of magnetic experiment in the lab. And then they'll say, vary the temperature and see what do they get for the magnetic order as a function of temperature, right? Or they might vary the applied magnetic field and see what's the magnetic order as a function of applied field, okay? So now my goal is to make a prediction for this magnetic order parameter as a function of temperature and applied magnetic field. And then this is going to be a prediction that somebody can test in the lab. Okay, so the magnetic order parameter, I should say, it depends on temperature, magnetic field. It also, of course, depends on J, the interaction strength between nearest neighbors inside a material. Right? Now, in a typical experiment, you can't change J. Right? In a typical experiment, the interaction between different sites, that depends on what kind of material you're working with. But that sort of thing is hard for an experimenter to change, right? Whereas temperature and magnetic field, those things are easy for an experimenter to change. All right, so let's think about how we can try to calculate this quantity, try to make predictions for it. the way that we make predictions is different depending on whether there are interactions between neighboring sites. Okay, so if we go back to the equation that we have for the energy here, okay, there are two different kinds of terms, right? There's the term here, which just has to do with each site individually interacting with the magnetic field. And there's a term here, which has to do with interactions between neighboring sites. Okay? Now, I'm going to show you this term is relatively easy to work with. This term is actually quite hard to work with. Okay? Now, I'm going to start with the easy thing first, and then work my way up to dealing with the harder thing. Okay? So, to begin with, in this class today, I'm going to consider the non-interacting Ising model, which means J equals 0. Okay? So that the only thing in the model is negative h times the sum over sites of this sigma I. Okay? This is what I'll do for today, and then later on in the next class I'll talk about how to put in the interactions. Okay, now there are a couple of different ways that you can solve this problem. Okay, and in the book I first talk about a standard solution, which is like what most people get in statistical mechanics or thermal physics courses. Okay, that's kind of the simplest solution to this problem, but I'm not going to do it. I'm going to do a harder solution. Okay, and I'm going to do a harder solution because it is going to be generalizable to the case with interactions. Okay, so I'm going to do a solution now in terms of energy and entropy. So this is kind of unnecessarily difficult to solve the non-interacting problem, but it's going to be generalizable. You can just take my word for that. Okay, so for this solution, I want to go back to the kind of consideration that I showed you in the last class about grouping together of states, classifying microstates into macro states. Okay, and so here I want to do this kind of a classification. Okay, I want to classify all possible states based on the number m. Okay, this order parameter that I just defined for you. Okay? I want to classify states based on how many spins are pointing up and how many are pointing down. Okay, so I want to say how many states go into the macro state, how many microstates go into the macro state with a particular value of m. Now, in order to do that, I want to say, each value of m is associated with a certain number of spins pointing up and a certain number pointing down. Okay, so how many, right? Well, from the equation that I just wrote here, right, we know that n up minus n down is equal to n, the total number, times m. Okay, and we also know that n up plus n down, that's the total number of spins in the whole lattice. Okay, this is two equations and two unknowns for n up and n down. Okay, and if I just want to solve these equations, I could say, well, I'll just show you the solution, that n up is the total number n times 1 plus m over 2. And n down is the total number n times 1 minus m over 2. All right, and you can check whether I got this solution correctly by taking these solutions and plugging them here and calculating what's the difference and calculating what's the sum, and you get the right answer. Okay, so when I want to classify states based on m, that means the same thing as classifying states based on n up and n down. Okay. Or another way to say the same thing is classifying states based on the probability that a spin is up. So that's n up over n. So that's 1 plus m over 2. And likewise, p down is n down over n. So that's 1 minus m over 2. Okay, so we could say how many states, how many microstates have n up spins pointing up and n down, so this is pointing up, and n down pointing down. Okay. This is a combinatorial question. Okay. So this is a question where we say, you know, if I have n spins in the whole lattice, I want to partition the n spins into a group of up spins and a group of down spins. Okay? And I want to say, how many ways are there to put n up of the spins in this group and n down of the spins in that group? This is the kind of thing that students often learn in a probability and statistics course. Can I ask you, has anybody taught you probability and statistics or how to do that sort of a problem? I'm seeing some favorable looks and some not so favorable. Okay. You know, the answer to this question is what people call the binomial coefficient. American students often will say this as n choose n up, right? Or n choose n down, right? And so what that means is how many ways if you have n objects, are there to label n up of them as pointing up and n down of them as pointing down, right? So that is to say, if I have n spins and I want to have 6 of them pointing up and 3 of them pointing down, okay, out of this 9, right? Well, there are lots of ways to do it. Let's see, I think I'll choose these 6 to be pointing up and those 3 to be pointing down. But I could have made lots of other choices. So this thing is equal to n factorial over n up factorial times n down factorial. Now, some students will say to me, this is something that they've seen many times long ago. And other students will look at me like they have no idea of what I'm talking about. Do people want to ask questions about this? Do people feel sort of familiar with this? Do people know what this factorial means, right? When I have the exclamation point, okay? It doesn't mean n, and I love n, right? It means n times n minus 1 times n minus 2, right? Multiplying all the way down to 0. I'm going to proceed as if people know what I'm talking about, but if you don't know what I'm talking about, please, ask me, and you can ask me now, or you can ask me separately, and we'll talk about what goes into this. Okay. So this is the answer to the question of how many microstates are in this macro state. Okay, so this is the classification problem, right? And so if I want, then I can say, what is the entropy of this macro state, right? I can say the entropy of the macro state with a certain value of m. That is, in other words, the entropy of the macro state with n up that are going up and n down that are pointing down. Okay. This is the thing that I tried to derive in an abstract way on Monday in the last class. Okay. So we had this general consideration, which says that the entropy is Boltzmann's constant times the natural log of the number of microstates. Okay, so when we apply that to this problem, it tells us that the entropy is Boltzmann's constant times the natural log of this binomial coefficient, n choose n up. Okay. Now, let's see if we can simplify that expression. Okay. So this is Boltzmann's constant times the natural log of n factorial divided by n up factorial, n down factorial. Okay. Now, if we use properties of the natural log, okay, so that's the log of n factorial minus the log of n up factorial minus the log of n down factorial. All right. This expression looks like it might be difficult to simplify, right? If what you know about n factorial is that it's this product of n times n minus 1 times n minus 2, et cetera, going down to 1, that looks difficult to put into a logarithm, but luckily there is a formula which gives us a good approximation to this. Okay, that is called Stirling's formula. And that is that for a large n, so n much greater than 1, the log of n factorial is approximately equal to n log n then minus n. And likewise, the log of n up factorial is approximately equal to n up log n up minus n up, and the same for n down. Okay, so this is actually an excellent approximation when n is a large number, and you know, a typical crystal might have 10 to the 23rd spins in it, so which is an enormous number. And so this formula works extremely well. Okay? So let's put that formula into the equation for the entropy. Okay? So it gives us that the entropy then is equal to Boltzmann's constant times, well, first I had the log of n factorial, okay? So that's n log n minus n, okay? And then I have to subtract off the log of n up factorial, so that's subtracting off n up log n up plus n up. Okay. And then I have to subtract off the log of n down factorial. So it's n down log n down plus n down. Okay, good with this? All right, now let's simplify that a little bit, right? Because we can cancel off that n is equal to n up plus n down, all right? And so now what? Now maybe I can factor out an overall factor of n, okay? So I'll say Boltzmann's constant times n, and then there's a log n minus n up log n up divided by n minus n down log n down. Okay. And let's see, I can now simplify a little bit more using properties of the logarithm, right? I could say, let's write this as kn, there's this minus n up over n, there's a log n up minus log n, right? So I'll put part of the log n from there into there. And the rest of it, I'll put over here. I'll say log n down minus log n. Okay. And so this is, let's see, Boltzmann's constant times n minus n up over n log n up over n minus n down over n log n down over n. All right. Incidentally, you do know I post the PDFs from what goes onto the whiteboard on the Blackboard page, and so you don't have to be frantically trying to copy down equations. You can always check the PDFs later. And so you can concentrate on things like trying to catch me making mistakes, because I know when I was a student, that was just the highlight of my day, was when I could catch a professor making mistakes, and I'd be so excited. Right? And so I don't want to deprive you of that pleasure. Okay, so this is all equal to Boltzmann's constant times n, let's see, minus p up log p up, or I could write that as p down log p down. Or, remembering that we derived something for those probabilities over here, right? So if I want to take those expressions and put them into my entropy equation, yikes, back to the pen.
I guess this is the definition of Shannon entropy, right?
And this is, yeah, that's right. This is the same as the Shannon entropy. So minus 1 plus m over 2 log 1 plus m over 2, and then minus the same thing, 1 minus m over 2 log 1 minus m over 2. Yeah, this is the same as the Shannon entropy, which is a concept in information theory. Okay, so all right, here's a nice equation for the entropy, okay? And it depends on m. Okay, so this is kind of what I was looking for. I was looking for an expression to say, if I'm classifying the macrostates, I'm classifying the microstates into macrostates based on what's the number for m. Here is the entropy of that associated with that value of m. So this is part of the free energy, right? The point of the class that we had last time was that there's a free energy, which is kind of a correction to the regular energy, okay, which has to do with the multiplicity, right? And so here is the multiplicity that's involved, right? That's characterized by the entropy. Now, there's one other piece which I can also describe here, okay? And that is the regular energy, okay? So the energy associated with all the states with this magnetic order parameter m, okay? Well, we know that is minus h times the sum over all the sites I of sigma I. Well, what is that? Okay, well, here, this is all the sites that have spin up have sigma equals +1. And how many sites are there like that? Well, n up of them. Okay, so there's n up sites with a +1. Okay. The other remaining sites, there are n down sites where the sigma is -1. Okay. So this quantity is -h times n up minus n down. So that's the same as -h n times this order parameter m. So now I know the energy associated with the magnetic order parameter m. I also know the entropy associated with m. So I can combine those things and get the free energy associated with the magnetic order parameter m. So that gives us that F of m is the energy minus temperature times entropy. So that is minus HNM minus temperature times entropy. So using this thing, and I'll cancel the minus signs, it's this plus KTN times 1 plus m over 2 log 1 plus m over 2 plus 1 minus m over 2 log 1 minus m over 2. Okay, so for the Ising model with no interactions, okay, here's an expression for the free energy. And in many cases, well, I should say this free energy depends on a couple of things. Okay, so one thing that it depends on is temperature. Another thing is magnetic field. And then it's proportional to the number of sites in the system. And it involves this magnetic order parameter in kind of a slightly complicated way. So we might want to know, how does this depend on the magnetic order parameter? Okay. And so that is something which I can plot for you. In fact, I have a nice Mathematica notebook. So I'm going to switch my screen from the whiteboard to the Mathematica notebook. Okay, so I'm going to stop that screen sharing and I'll start a new screen sharing with the Mathematica notebook here. Share. You guys see that now? Okay. Here is a plot of the entropy. So this quantity right there, okay, you see the things I highlight, right? Okay, this thing that I just highlighted, this is the entropy that we calculated. Okay? So here's entropy on the vertical axis as a function of the magnetic order parameter on the horizontal axis. You can see that this looks like approximately an upside down parabola, right? It's not exactly a parabola, but it's pretty close. Okay? And so you can see here that the biggest entropy is if m equals 0. Okay, so if I say have 100 spins, there's a lot of ways to have 50 of them point up and 50 of them point down. Okay, there's not so many ways to have all 100 point up and 0 point down. There's only one way to do that. Okay, so the entropy is higher if m is 0. It's lower if m is plus or minus 1. So I can put that into the free energy. Okay? So this is the Mathematica syntax to produce the free energy. Okay, and to be more specific, it's the free energy divided by k times t. Okay, so that's a normalization in the plot. Okay, so this is the free energy, which includes both the magnetic field term and the entropy term. So this, in this particular plot, this is with the magnetic field equal to 0. So this plot is just the negative of this one. Okay, so this is showing us that when the magnetic field is equal to 0, the state with the lowest free energy is right here with m equals 0. Okay, because that has the biggest entropy, so it's the lowest free energy. And so what I argued in general in the last class is that the system tends to go to the state with the lowest free energy. So if there's no magnetic field, the system tends to go to m equals 0. Okay. But what if there's a magnetic field? Okay, so here I put in a magnetic field divided by kT of 0.3. In this case, you can see now the plot is asymmetrical. The minimum is no longer at m equals 0. Instead, the minimum is over here at some positive value of m. That means when there's an applied magnetic field, you tend to get this positive value of m. Okay? And then here's my cool Mathematica trick for the day. Okay, here is a plot of the free energy with a little slider to control the magnetic field. So you can see if I make the magnetic field be positive, the minimum shifts over to a positive magnetic order parameter. So if I put on a magnetic field pointing up, the spins start to align, mostly pointing up. And if I put on a magnetic field pointing down, so here's a negative value of the magnetic field, then the spins tend to align, mostly pointing down. Right? So this is, and here, if I click on this plus sign, it shows what's the number for the magnetic field divided by kT. So this is graphically showing us what's going on. It's graphically showing us that the free energy plot changes when we change the magnetic field. And the minimum shifts when we change the magnetic field. So the minimum can shift from being negative m to 0 up to positive m. So this is kind of a graphical solution. Okay? because I'm out of time now, I'm going to have to stop here for today, and then I'll show you the algebraic solution in the next class. Okay. So I'm going to stop talking for today now, but I'll be very glad to answer any questions, and otherwise I'll see you on Friday.